And that's it for day 12. If you want to see my code, it's linked to down in the description as usual. And if you have any questions or comments, feel free to leave them in the comments below. I'll see you tomorrow for day 13. Thanks for watching. All right, in this video, we're going to be doing day 12 of Advent Code 2024 garden groups. So first, live video of me solving the puzzles. All right, so today we are tasked with finding a bunch of different plots inside a garden. So the garden has a bunch of different plants, and each of them is denoted by a separate letter arranged in a square grid. So for example, this might be a garden, it's a 4x4 garden, and there are five different plots. So we have this contiguous plot over here of A plants. We have this 2x2 plot of B plants. We have this Tetris block shaped plot of 4 C plants. We have the singular D plant, and we have these 3 E plants. The task is to find the perimeter of each of these plots, multiply it by the area, and then sum up all of those products. So the perimeter is determined by basically adding up the number of sides of the shape. So for these 4 A's, the perimeter is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then for this D, for example, the perimeter would be 4. Area is pretty simple. It's just the number of plants inside. And we have to find all of them for all of the different plots. So to do this, I use some depth first search. Essentially started it at every single point, and then just did a BFS or a DFS to check all of the connected plants inside the grid. And then to compute the area, once you get that, I wrote this little function, which I guess I'll explain down here in a bit. The idea is you just count the number of free cells next to every point inside a plot. And the number of free cells is basically the number of neighbors, which are not the same. And that's how you get the perimeter. To get the area is just the number of things inside that plot. Now, to get into the details of the DFS, essentially we have this scene set, which keeps track of the number of, or like which cells we've seen as the row column coordinate. So as we iterate through every cell in the grid, if we've already hit a cell, for example, if we've seen it in a previous plot, then we don't want to consider it anymore. We just continue. Otherwise, we're going to initiate a new plot, which we keep track of in this plots list, which is a two-dimensional array where the first element of every row is the character that is in the plot, or like the letter, which is the plant designation, and the second is a list of all the coordinates that belong to that plot. So here's the debugging statement, and here's the actual DFS. So we initialize a stack, which is the starting coordinate, and then while the stack is not empty, we pop off the top element. We see, oh, has this already been seen? If so, then we don't want to consider it. If it's not within the bounds of the grid, we also don't want to consider it. If this element is not the same plant as the one that we're doing the DFS from, then we also don't want to consider it. Otherwise, it satisfies all three of those properties. It's within the grid. We haven't seen it yet, and it's the same plant that we want to consider. If all of those are satisfied, we add it to scene, and then we also add it to the plots array to say, yes, this plant is part of the plot that we're currently looking at. And then we go through all of its neighbors to add them to the stack and continue the DFS. So at the end, we have this list plots, which is two-dimensional. We iterate through it to get the perimeter of every single plot. And that's with this function over here, perim of plot, which takes in a list of coordinates and returns the perimeter of that shape. So that's done using this count free function, which takes in a coordinate. And I guess this argument is not really necessary. It's computes for all of the neighbors of this coordinate, how many of them are not the same character as that coordinate. So we use this DD array over here, something that I've used quite often, same variable name, basically just the 4 different cardinal directions, differentials for the row and column, so you can iterate through neighbors more easily. Go through all of the neighbors, check if it's within the grid. If it's not within the grid, that's considered a free neighbor, so it's a neighbor that is not the same as the current cell, which contributes to the perimeter. Otherwise, if the neighbor is not the same as the original cell, so it's within the grid but it's still not the same character, that also increases the perimeter. So this just tells us how many neighbors are not the same as the current one, and that contributes to the total perimeter of the cell. Add all of those up, and then to get the area, we just get the total size of the plot. So the number of coordinates within a plot is the same as the area. Multiply perimeter and area, add that to the answer, and that's it for part 1. For part 2, we get some bulk discounts. So instead of having to pay for every single unit of perimeter, we can pay for all straight edges at once. So for example, here, A, this only has 4 sides, so its perimeter is technically only 4 for part 2, because even though the ones on the top and bottom are 4 units each, they're all straight lines, so we only need to pay 1 unit of perimeter for each of those. One interesting edge case here is if you have like this A region, this contiguous A region, and it has a little like line that splits down the middle here and turns left, and then you have another line which comes up and then turns right, and they intersect at the same point, those technically count as 4 different edges. So you can't use 2 pieces of fence to cover both of them. You do need to get 4 separate pieces of fencing, which is a little bit strange, but I guess it kind of makes sense if you want like a contiguous fence shape. Yeah, so to do this, the insight that I had was to note every 2x2 subgrid within a plot and then look at what the pattern is. So, hang on, part 2. Yes. So, for example, let's magnify this input, enhance. So, let's look at the R's, for instance. So, for every 4x4 or the 2x2 subsection of the plot, you can tell whether there's a corner or not by the fact that there exists only 1 or 3 R's. So for example, if you look at this little subsection, I can't highlight it contiguously because of the restrictions of editors, but if you look at these 2 R's and this VR down here, this rectangular section, there is a corner here because there's a fence that goes along vertically here and horizontally here and vertically here. And that's because there is 1 piece that doesn't lie inside the plot and 3 that do. So that defines a sort of, I guess, concave edge. Another case is if you have 1 that lies outside and 3 that lie inside. So for instance, let's see, this R, I suppose, if you took this 2x2 plot, so this IR, and then the 2 above it, you would have 2 empty slots, an R and then an I. So that would also count as an edge. This is more of a convex edge, but you can notice it goes kind of vertically here and then horizontally here. So basically, we just have to look at every 2x2 subplot within a plot and see how many corners each of them contributes. So we did the same thing as part 1. This is still the same DFS. And count free also exists, although I don't know if we use it at all. Yeah, we don't use it, so we can just delete it. The only thing that needs to change is this perimeter function. So it takes in plot, which is a list of the coordinates that are within a plot, and we just need to tell how many corners there are, because the number of corners is the same as the number of edges for any polygon, so we just need to count the number of corners to get the total number of pieces of fence that we need to use. So I also have this little function here within that perimeter function to basically give us a set of coordinates, and it returns 1s and 0s based on whether every coordinate is within the plot or not, just for the sake of, I guess, compactness when writing the code, because we'll get to this later on. But for example, if you enter 10 different coordinates that are all within the plot, it will return 10 1s. If the first 5 are within the plot and the next 5 coordinates are not within the plot, it will return 5 1s followed by 5 0s. In this case, we're only going to use it on 4 different coordinates because we're going to be testing these little 2x2 blocks at once. But this function is just useful for compactness of code. Over here, this is just an optimization, not really necessary, but we get the bounding rectangle for the current plot, which reduces the number of 2x2 subplots that we need to look at, but that's not really necessary. So now we go through all 2x2 plots by looking at the top left coordinate. We start with the minimum coordinate -1, because we also want to check outside the grid, because remember, for example, this top left R is a corner, and the only way you would get to that is by checking the 3 non-existent squares to its left and upwards, as well as the current square, so we do need to do that -1. And then we also have the -1 for the column over here. That's not really a necessary variable. So we test the 4 coordinates that we care about, which are in this 2x2 grid, and then these are all the patterns that contribute to 1 corner. So the order is top left, top right, bottom left, bottom right. If it's 1 0 0 0, that means the top left is inside the plot and the other 3 are not. This is a convex edge. This is if the top right is in the plot and the other 3 are not. That also defines a convex edge. And the same goes for these 2. They're just different rotations of that same case. The other case is a concave edge, where we have 3 that are inside the plot and the 1 that's not inside the plot. That's these 4 cases. And then recall there's also the edge case, where we have 2 sort of overlapping corners. So in this case, we have a corner here and a corner here. And that happens if there are 2 inside and 2 outside that are diagonally opposite. So that's these 2 cases. For this top one, this is top left, bottom right. And this one is top right, bottom left. So if either of those happen, then we need to add 2 to the total number of corners. And that's this expression over here. So at the end, we just return the total number of corners, and that's the same as the perimeter because it's a polygon. So multiply that by the area again, and that's it for part 2.